Example problems with fluid dynamics. First problem. A cup is filled with water to a height h. You poke a very tiny hole in the bottom of the cup. How fast will the water come out of the hole? So here's what we've got. We've got a cup, all right, and it's filled up with water to some height h. We're going to poke a little hole in the bottom and let water come out. All right, so this is just like water flowing through a hose and then it goes through a nozzle, right? We have a big cross-sectional area here, the water flows through, and then it's squeezed through this little nozzle down here. All right, so now we're going to, because this is Physics 123, we're going to make some assumptions. We're going to assume that the flow is irrotational, there's no turbulence, and that it flows laminarly. We're going to assume, being water, that it's relatively incompressible, so that we're able to use the equations that we use in this course. All right? The first equation we're going to use is the continuity equation. A1V1 is equal to area 2 V2. So let's let this be 1 down here and 2 up here. Okay? And then we've got Bernoulli's equation. Pressure 1 plus rho g y1 plus 1/2 rho v1 squared is equal to pressure 2 plus rho g y2 plus 1/2 rho v2 squared. Okay, so let's look at stuff here. All right, what is it that I want to find? I want to find how fast the water is coming out of the hole. So I want to find V1 right there. Okay? What do I know? Do I know the pressure at the top? Well, presumably the cup is open to atmospheric pressure, right? So it'll be atmospheric pressure at the top. The hole at the bottom is open to atmospheric pressure. So I know then that the pressure at the top is going to be the same as the pressure at the bottom. So these two will cancel out. Okay? Now, that is a little easier. I don't know y1 and I don't know y2, but I do know their difference, right? So I think I'll be okay there, because I'm going to end up, when I solve for this, I'm going to end up taking those to the same side and I'll end up with just a difference. All right? So I'm not too worried about those two. But what about V2? I can find V2 in terms of V1, the thing I'm trying to find, using the continuity equation, except I did not give you an area for my hole or for the top of my cup. That seems problematic, doesn't it? Okay, so we're going to have to make some assumptions here. I said it's a very tiny hole, right? What does very tiny mean? It means that A1 is much, much smaller than A2, all right? So if A1 is much smaller than A2, that means that V1 is going to be much larger than V2. So what we're going to do is we're going to say, well, V2 is essentially really close to 0. So we're just going to throw this term away, all right? Because we said it's a very, very tiny hole compared to our, the diameter of our cup. All right? So with that, then, I can solve this equation for V1. First, let's take this term here, but let's take this one to the other side, and then we get rho g y2 minus y1. All right? But y2 minus y1 is just this height, h, right? So it's just rho g h. Excellent. All right, and then we're going to cancel out the rho on both sides. We'll take the 2 over to the other side, so it's v1 squared is equal to 2gh. And then I take the square root of both sides to find v1, and it's just the square root of 2gh. All right, do the units work? Well, let's think about it. G has units of meters per second squared. H has units of meters. So I get meters squared per second squared. Take the square root, I get a velocity. Okay, it looks good. Let's move to our next problem. A pump pushes water through a hose where it exits the hose at a height of 10 meters above the pump with a velocity of 3.2 meters per second. If the air surrounding the hose has a pressure of 1 atmosphere, what is the pressure in the hose near the pump? Okay, so we've got a pump, and it's pushing water up a hose, and some height, h higher, the water comes out with some velocity v. We'll call this v2, all right? I'm not given the diameter of the hose, but I do know it's the same, right? And we didn't say anything about it being some sort of weird hose whose diameter changes, so we'll assume that the cross-sectional area is constant, all right? From the continuity equation, A1 V1 is equal to A2 V2, so we know that if these two cross-sections are the same, the two velocities are the same. So the velocity down here is the same velocity, v2. All right? We know the pressure out here, all right, pressure 2, and we're trying to find pressure 1, right? So let's write down Bernoulli's equation. Pressure 1 plus rho g y1 plus 1/2 rho v1 squared is equal to pressure 2 plus rho g y2 plus 1/2 rho v2 squared. All right? And we said, well, look, these two velocities are actually the same, so they cancel out. We get rid of that. And then we can just find pressure 1. We solve for this. It's just going to be pressure 2 plus, we bring this to the other side, and we're just going to get rho g y2 minus y1. Well, that right there is just h. And we have our solution. Everything here is known, right? Everything now is known. We plug it in, we get our answer. One weird thing, notice that, okay, well, first let's check units, right? Rho g, we know that rho g meters has units of pressure. That's just Bernoulli's equation. So everything has units of pressure. We're good. Okay? We could plug numbers in and see if we get something reasonable. I'm not going to plug the numbers in. Another thing we can do, though, is we can check the units. Let's just check the units. What am I saying? Never mind. We check the units. We plug numbers in. Hopefully there's something reasonable. We could take some limits, right? What if the height were 0? What if the height out was the same as the height at the bottom? We'd say, well, the water's just flowing through the hose at constant pressure then, right? If there's no viscosity, no turbulence, then we should get the same pressure, and in fact this term goes away. If we increase gravity, the pressure we need goes up. That makes sense. If the fluid has more density, this column of water will be heavier. We need more pressure, so that makes sense. It looks like we've got the right answer, despite the fact that it doesn't depend on this velocity that we were given, all right? It turns out this is correct. Your answer shouldn't depend on that velocity. Shouldn't it take more pressure to make the water flow up the hill faster? Well, the point is, well, no, it doesn't, all right? And Bernoulli's equation is right. The pump does have to work harder, though, right? So the pump has to work harder because if I want the water flowing out with some kinetic energy, it has to go in with some kinetic energy. So the pump works harder to make the fluid flow faster, but it's not because it's increasing the pressure down here. It's increasing the initial velocity of the water, so it comes out faster, all right? But there's our answer. One more quick problem here. Water flowing through a hose with a diameter of 1.5 centimeters passes through a nozzle with a diameter of 0.2 centimeters before exiting into the air. If the air has a pressure of this and the pressure of the water before it enters the nozzle is that, how fast is the water going when it exits the nozzle? So we have our nozzle, all right? We're given the diameter, right? We're given the diameter here, and from that we can easily find the cross-sectional area, right? We are given the pressure here. We're given the diameter over here, from which we can find the cross-sectional area here, and we're given the pressure here, all right? And we want to find the velocity. How fast is the water going as it exits the nozzle? That's the same as the velocity inside the nozzle, all right? So we just need to find the velocity inside the nozzle. Write down Bernoulli's equation, P1 plus rho g y1 plus 1/2 rho v1 squared is equal to P2 plus rho g y2 plus 1/2 rho v2 squared. These two heights are the same, right? We didn't say anything about, I mean, it's just a small thing. We just want to know as soon as it gets into the nozzle how fast it's going, right? So presumably we didn't say anything about any height difference in the problem, so we're going to assume the height here is the same as the height there, and those two terms go away. We're given the pressure in the hose, we're given the pressure in the nozzle, or in the air, right? And the pressure in the air is going to be the same as the pressure in the nozzle because the diameter of the flowing water is the same in the nozzle and when it comes out into the air. So this is just air pressure. This is the pressure we're given. We want to find the velocity in the nozzle. We want to find that velocity right there, but we don't know that velocity right there, so we have one equation, two unknowns. Our other equation, of course, is the continuity equation. All right, and the cross-sectional area is just pi r squared, right, which is diameter over 2 squared times v1. And then the air cross-sectional area in the nozzle is just going to be pi diameter in the nozzle over 2 squared v2. All right, and then we cancel out our pi's, and we find then that v1, the thing that we don't want to find, we can find in terms of the thing we want to find. It's just going to be v2 times the diameter of the nozzle divided by the diameter of the hose squared. Okay? And then you just plug that in for V1, and then you've got an equation with just one equation, one unknown, and I'll let you do the rest. All right? After you do it, check, make sure your units work, make sure that things work the way that they should. If I make that nozzle diameter smaller, the velocity ought to get bigger, right? And things like that. So, you know, take limits, and the limit is the two have the same diameter, then we've got a problem, all right, because our pressures are different. So that can't happen. All right, but think of different ways to look at the problem and see if you get the right answer. Another thing you can do, once you get your final velocity, pretend like you knew the velocity, but you didn't know the pressure in the hose. And go and solve the problem as if you didn't know the pressure in the hose and see if you get the pressure that was given. So practice the techniques we discussed and are written in the syllabus to make sure you get your answers right.